This lecture is about using area under the curve to test the difference between two independent means. In the previous lecture, we created confidence intervals for each of the two sample means, for method A and method B, to determine whether we could reject the null hypothesis, which stated the means for the two methods are equal. We would fail to reject the null hypothesis if the confidence intervals overlapped, or overlap by more than a little bit. And we would reject the null hypothesis if the confidence intervals do not overlap, or only overlap a very little bit. Now, we will use area under the curve to determine whether the difference between the two means reflects a true difference in the population means or is just due to chance, due to sampling error. In this example, the question is the mean social adjustment score different for boys and for girls? The IV is gender, and the DV is social adjustment. And we want to know, is the difference between the means big enough relative to the standard deviations for the means to support rejecting the null hypothesis? The null hypothesis states there is no difference in the mean social adjustment score for boys and for girls. And we're going to test whether the difference in means that we observe in these two groups in our sample is big enough to reject the null hypothesis. We assume the null hypothesis is true, unless we have sufficient evidence to reject the null hypothesis. The null hypothesis is about the population. We use data from our sample to test the null hypothesis. If the chance that the null hypothesis is true is very small, we have sufficient evidence from our sample to reject the null hypothesis. When testing a hypothesis about the difference between two means, we are testing whether the difference between the two means in our sample is big enough to provide evidence to reject the null hypothesis. In other words, what is the likelihood that we would see a difference in means in our sample this big if the null hypothesis is true? We determine the probability of obtaining this difference between the two means observed in the two groups in our sample under this assumption that the null hypothesis is true. We use area under the curve for the t-distribution to determine this probability. And this is based on the sampling distribution of the difference between means. Just as we had a sampling distribution around a single mean, now we're looking at a distribution of differences between the means for many hypothetical pairs of samples. We assume our sample is a very good, albeit not perfect, representation of the target population. And this is a reasonable assumption if we selected a sample using rigorous sampling methods. If the difference between the two sample means is 0, in other words, no difference, then the chance that the null hypothesis is true is pretty certain. If the difference between the two sample means is small, well, then there's still a pretty high chance that the null hypothesis is true. But if the difference between the two means in our sample is big, then the chance that the null hypothesis is true is very low, and we would reject the null hypothesis. When there is a very small likelihood that the difference between means in our sample could be obtained if the null hypothesis is true, we conclude the null hypothesis is very unlikely to be true, and we reject it. We conclude that the difference that we observe in the means in our sample is not just due to sampling error, that this difference in the means in our sample reflects a true difference in the population means. Well, at what point do we come to this conclusion that we have enough evidence to reject the null hypothesis? That point is called the significance level, or alpha. We set alpha based on how confident we want to be when we reject the null hypothesis. Usually we set alpha at 0.05, so we are 95% confident when we reject the null hypothesis. Now this means there's a 5% chance that we're wrong when we reject the null hypothesis, but we are willing to live with that degree of uncertainty, that 5% chance that we could be wrong, in order to be able to practically conduct tests of hypotheses.